Okay, so first of all, I would like to thank the organizer for inviting me to participate in this school. I'm going to talk about traveling waves, near shear flows for 2D Euler, and everything that I'm going to say today here is a joint work with Daniel Lear. So this is 2D Euler equations for an incompressible flow. I don't know if you know it. For me, B is going to be the velocity. I'm going to call to the vorticity W with this convection for the sign. We are going to work mainly in the domain T times R and also in a periodic channel. So here T is going to be a periodic function, 2 pi periodic function in the horizontal variable. So we fix the period to be 2 pi. And a shear flow is something like this. It's a velocity with a second component equal to 0 and with first component just depending on the vertical variable y. Okay? And it happened that these shear flows are a stationary solution for 2D Euler. Okay? Some famous examples of shear flows that I am going to consider in this talk are the following: the flow, where the velocity is given by y. I am also going to say something about the Taylor-Couette flow, which is not a shear flow, but it's a kind of. The Taylor-Couette flow is given by this expression. You pass to polar coordinates, and then you take the radial component of the velocity equal to 0, and you take the angular component of the velocity in this way. And what you obtain is also a stationary solution for 2D Euler. Okay, these coordinates. Then, in the last part of the talk, I will talk about the Poiseuille flow, where the velocity is given by y squared. And well, I also comment something about the Kolmogorov flow, but I will not say many new things about it. Okay, let me start with the Couette flow. So we are interested in finding solutions, traveling wave solution close to this shear flow, and then I'm going to write the velocity v as the velocity for the Couette flow plus a perturbation u that you can think of it as something small. Then the full vorticity w is given by -1 plus the perturbation omega that is also small. And you arrive to a transport equation for omega, which is written over here, where the velocity u is given by the perpendicular gradient of this inverse of the minus Laplacian, of the Laplacian, which is, if you are working in this domain, T times R, you can write in this way. Okay? My convection is that the perpendicular gradient is given by this operator. Something that I would like to emphasize here is that the equation for the perturbation omega is a transport equation for a perturbation of the Couette flow, but it's not a transport equation if you consider a general shear flow, because for a general shear flow you have this term over here which breaks the transport character of the equation. Okay, this is going to be important in this talk. Okay, so on Sunday, this slide was full of reference. On Monday, I added one more. I did the same on Tuesday, and yesterday, I removed all of them. So I think that Michele and Tarek, they did a great job, and I don't have many things to add. Let me just remind you that the Couette flow is stable if you work with in Gevrey spaces, which are spaces of very high regularity, and that if you go below this regularity, then you can find some instabilities arbitrarily close to the Couette flow. Okay, this is a work by Juden and Nader Masmoudi, and also by Juden and Christian Zillinger, that they work in the linear case. Okay, so main topic of this talk is the system of traveling wave arbitrarily close to the Couette flow, and what we know about this. So I'm going to comment on two papers. The first one is this paper by Lin and Lin, where they find traveling waves arbitrarily close to the Couette flow at the level the vorticity in L2. Okay? So if you measure the distance to the Couette flow in L2, they are able to find that arbitrarily close to it, there exists some traveling wave. Okay? And the way they do it is that they consider that the velocity v1 is equal to y, the velocity of the Couette flow, plus a perturbation u1. And this perturbation u1 is given by this form. Okay? So they are able to show that there exists some traveling wave bifurcating from this velocity v1 for any number n. Okay? Then if you take n very, 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 very large, this function is close to 0 in L2, and then this velocity is close to the Couette flow in L2, and since you are finding traveling wave bifurcating from it, so then you are finding traveling wave solution which are arbitrarily close to the Couette flow in L2. Okay? This is the strategy to prove the system of traveling wave that these two authors, Lin and Lin, use. So let me comment that they work in a periodic channel, okay, with upper and a lower boundary. And then Lin and Zen, they prove the following result. They prove that there exist stationary states arbitrarily close to the Couette flow in the H3 half minus topology. So here, 3 half minus means that give me an epsilon, and then I can find stationary states as close as you want to the Couette flow in the space H3 half minus epsilon, okay, for any epsilon bigger than 0. And they were also able to prove that if you measure the distance in H3 half plus, then there is no non-trivial traveling wave arbitrarily close to the Couette, traveling wave arbitrarily close to the Couette flow. Okay, and here trivial means that the dependence on the x variable is trivial. Okay, so in these two papers they work in a channel, and what we did is to prove that there exists a traveling wave arbitrarily close to the Couette flow in the same space H3 half minus. Okay. Well, for us, a traveling wave is something like this. It's a vorticity whose dependence on time is just a translation of the first variable with a speed lambda. Okay. Non-trivial, again, means that dependent on x is non-trivial, otherwise we are working shear flow. Our solutions are C infinity for the perturbation omega and compactly supported. They have HS norm large for S bigger than 3 half, but they are smooth otherwise. And something very important is that the gradient of our vorticity is concentrated around these two lines, plus L and minus L. And then the speed of the wave satisfies something like lambda is equal to L plus order epsilon. Okay, so the speed is order 1 with respect to the distance to the Couette flow. Okay. So let me just make a very naive comment. So if B is a solution of the 2D Euler equation, then just by Galilean invariance, if you consider this velocity V bar, given by this expression in terms of P, this is also a solution. Okay? And then if you pick one of these stationary solutions of Lin and Zen, then this V bar is a solution of 2D Euler and is a traveling wave. So the system of a traveling wave arbitrarily close to the Couette flow is already proven by Lin and Zen. But if you really want this velocity v close to the Couette flow, then you have to make this velocity lambda, this speed, of order epsilon. So in our case, lambda is of order 1. So in that sense, our solutions are different from this solution that Lin and Zen found in their paper. Okay? So let me comment a little bit how we prove the system of this traveling wave close to the Couette flow. First thing we do is that we understand the 2D Euler equation as an equation for the level sets of the vorticity rather than an equation for the vorticity itself. Okay? And we assume that we can parameterize the level set of the vorticity. This is an assumption that we do, and actually is something that we impose in the initial data. We assume that the level set are going to be given by a family of graphs. Okay? And then you have that the vorticity along these families of graph is equal to a function, varp, a profile, that just depends on y. Okay? One may think that this profile should also depend on time, but because of the transport character of the equation for the perturbation omega, we can assume that this profile is time independent. Okay? From this expression, you can recover the gradient of the vorticity in terms of the gradient, well, the derivative of the profile varp and the gradient of the graph f's. And taking a time derivative and using the equation for the perturbation omega, one can arrive to an equation for the level set f. And something very important here is that you are multiplying this equation by varp prime. And then we just need to solve these equations inside of the support of varp prime. So otherwise, the equation is automatically satisfied. Okay? Here, U comes from the Biot-Savart law, and we understand that U as an operator that acts on F and depend on the profile varp. That is something that we still have to choose. This is a degree of freedom on our method. It's something that we are going to fix later. Okay?
For example, there is no unique choice of graph.
Sorry?
There is no unique choice of graph.
No. This is for the perturbation, not for y, not for Couette.
Right.
It's the perturbation omega.
Okay. I think what do you fix when it's zero?
You don't need to fix anything because in the part where the gradient of the vorticity is 0, so the vorticity is constant and the solution is still constant. Okay? So for example, if you are here, let's say that here the velocity is constant and here the velocity is constant. Okay? And these are the level sets. Then the level sets are going to move with the flow. Okay? And you are going to have something here and something here. But here, the vorticity is going to be still constant with the same constant. Okay? And then you just need the equation for the level set inside of the support of the gradient of the vorticity that actually is related with the support of the profile varp prime. Okay.
So the choice of f can be terrible.
Yeah.
Zero.
Yeah. Okay. Then, if we are looking for a traveling wave solution, that means that our function f, well, the time dependent of the function f can be written as just a translation with the speed of lambda in the first variable. Okay, and if you introduce these answers in the equation, you arrive to this equation that you have to solve in the interior in t times in the interior of the support of varp prime. Okay, so this is an equation for both, for lambda and for the family of a graph f. And then if we call capital F to this guy, what we have to do is to find the zeros of this functional capital F that depend, of course, in the profile varp. Okay? And something very easy to check here is that for every lambda, F equal to 0 is a solution. Okay, and then this is the starting point to try to apply the Crandall-Rabinowitz Theorem in order to find a branch of solution bifurcating from this value f equal to 0 at some value lambda. Okay, so this is the Crandall-Rabinowitz Theorem. You have two Banach space, x and y. You have a neighborhood B around 0 on x. And you have a functional that goes from R times this neighborhood of 0 to 1. Okay? And you must have the following properties. For every lambda, f equal to 0 must be a solution. Then you have that the partial derivative understood in the Frechet sense of the functional capital F, d lambda df, and this second derivative, this cross derivative, d lambda f of f, is and are continuous. These are the only two conditions in the Crandall-Rabinowitz theorem that has to do with the nonlinear part. So third and fourth has to do just with the linear part, and they said that there exists a value lambda star such that the partial derivative with respect to f of the functional at the point f equal to 0 and at the values lambda star, which I'm going to call to this linear operator L star. So for this value of lambda star, this guy has a one-dimensional kernel, and also the codimension of the image on Y of this operator is one-dimensional. Okay? And for something which is called the transversality assumption, you have that if you apply this guy, the second derivative with respect to lambda and f, at the point f equal to 0 and on the values lambda star, if you make add this operator on H star, where H star is the element that expands the kernel of our operator L star, then this guy must not belong to the range of the image. Okay? If you have these four hypotheses, then you can show that then there exists a continuous branch of solution, lambda and f, in this space, bifurcating from the point lambda star 0 in the direction H star. Okay? Where H star is, well, here, the superscript star is the same than the superscript this asterisk. I don't know, I have used different, but everything is the same. Okay. Well, this is the Crandall-Rabinowitz theorem, and this is the main tool that we use in order to bifurcate, to find traveling wave solution close to the Couette flow. Okay. I'm not going to say very much about the proof of, about the application of this theorem to our result, but I'm going to explain a little bit how our profile bar P is. Okay? Because bar P is something that we still have to choose. And what we do in order to find, let's say, for example, an element in the kernel of this linear operator, the derivative with respect to f at f equal to 0 of our functional, is this profile bar P. Okay, it's going to be a trapezoid. The height of the trapezoid is epsilon, and it's going to be linear and goes from epsilon to 0 in an interval of type also epsilon. Okay. So this is going to be our perturbation. Well, there is a problem with this perturbation, is that it's not smooth, it's just Lipschitz. I'm going to explain how we solve this problem in the next slide, because actually we want to solve the system of C infinity traveling waves, so we need a C infinity profile bar P. But what is important for this profile is that it's small in H3 half-minus, okay? And then by making epsilon very small, you can do the norm of this profile in H3 half-minus as small as you want, okay? This is the main point. And in order to solve the problem with the regularity, what we do is just to smooth a little bit the corners, okay? We introduce a new parameter kappa, and we use this parameter to make like a smoothing of the corner in an interval of psi kappa epsilon. And then by making an asymptotic analysis in both kappa and epsilon, we are able to apply the Crandall-Rabinowitz theorem to our function. Okay? This is the idea. We can do more or less the same or similar things for the Taylor-Couette flow. So here, this is to the Euler equation written in polar coordinates. The velocity has again two components, the radial component Vr and the angular component B theta. And it happened that any velocity with this form, so B theta, Vr, the radial component is equal to 0, and B theta equal to a function that just depends on the radial variable, is also a stationary solution for to the Euler equation. Okay? And in this setting, the Taylor-Couette flow is something where the radial component of the angular component of the velocity is given by this expression. Okay, and we consider these equations in an annulus, something like that. R1, R2. And what we are able to prove is that arbitrarily close to this Taylor-Couette flow, there exists a time periodic rotating solution. They are a kind of traveling wave, but in this setting, actually you can see them like a rotating solution. Okay, and they are arbitrarily close to the Taylor-Couette flow. So the strategy is kind of the same. In this case, the level set must be a closed curve, and we choose this level set as something like this. And then you can arrive again to an equation for f. And in this setting, if you take that this function is actually something like that, well, you obtain a similar equation, but now for g. And you can use a similar property in order to get a traveling wave close to this Taylor-Couette flow. Okay, the strategy is a kind of the same that for the previous case. Okay, let me say something about the Kolmogorov flow. So the system of traveling wave and stationary states arbitrarily close to it had been studied in this paper, a stationary structure, near Kolmogorov and Poiseuille flow into the Euler equation by Michele, Tarek, and Klaus Wittmeyer. And they essentially prove the following. So if they work in a 2 pi delta periodic channel, and what they prove is that if delta is let's say 1, so then the period in the x variable is the same that the length of the length of the channel, and it coincides with the period of the velocity v1. Then they are able to show the system of stationary states which are as close as you want to the Kolmogorov flow, even this is quite strong. Even if you measure the distance to the Kolmogorov flow in spaces, in analytical spaces. Okay. However, if you take delta, let's say 1/2, then there is no traveling wave epsilon close in the H3 topology. Okay, they are able to reach H3. But we don't know if this exponent is optimal. Okay. So the Poiseuille flow has been also studied by same authors, Michele, Tarek, and Klaus. And they were able to prove a rigidity theorem. And what they prove is that there is no non-trivial traveling wave arbitrarily close to the Poiseuille flow in H5. Okay. So, and in the rest of the talk, I'm going to discuss. I'm going to try to discuss about the system of traveling wave arbitrarily close to the Poiseuille flow. Okay, this is a work in progress. We still have to do some job, but I expect to finish the paper soon. But well, I will tell you what we already have. So we work in a periodic channel. So T times minus 1, 1. We consider the equation for the full vorticity, W. In this case, if you look at the equation for the perturbation, this is not a transport equation anymore. And we want to still work with these level sets. And in that case, well, everything is much more complicated because you cannot assume that the profile is time independent. So in this case, we are going to work with the full vorticity. Okay. The velocity is going to be the perpendicular gradient of the stream function. And we are going to recover the stream function from the vorticity through this law. The Laplacian of the psi is going to be omega. And we are going to impose these boundary conditions for psi. In this way, we have two things. So with this boundary condition, B2 is equal to 0 in the lower and upper boundary. And this is something that we need because we want to have non-flux boundary conditions. And another thing that we have is that the circulation of our velocity, that is constant on time, is going to be the same that the circulation of the Couette flow. So we are going to construct traveling wave with the same circulation that the Poiseuille flow. And actually, with this relation of the vorticity and W, if you take W equal to minus 2y, which is the vorticity of the Poiseuille flow, what you recover is the velocity of the Poiseuille flow. Okay? This is the setting. And then we are going to do a kind of the same. We are going to consider that the level set of our vorticity are given by a family of graphs. And the vorticity along this graph is going to be this profile bar p epsilon that just depends on y. Okay, so and this profile is going to be minus 2y plus perturbation omega tilde epsilon. So omega tilde epsilon is not going to arise again in this presentation. So it's here just to make clear that if we take f equal to 0 and omega tilde equal to 0, then you work with the Poiseuille flow. Okay? And then if f is very small and omega is very small, you are close to the Poiseuille flow. Okay? This is the idea. In this case, we also have to add some boundary condition for the family of graph f, because you don't want to move the boundary. And we also assume that the family f has this form, so the time dependent is like this. And then we arrive again at an equation for lambda and for f, which is of the same form. So some functional, capital F, that depend on the profile bar p epsilon is equal to 0. And very important, we just have to solve this equation in the interior of the support of omega prime. Okay, this is essential in our analysis. Otherwise, we could not do that. And in order to apply the Crandall-Rabinowitz Theorem, we have to study this linear operator. Okay. So with this strategy, we are able to find, we think that we are able to find a traveling wave solution near this flow in H3 half minus. and we are sure that we cannot go further. So we could not reach a3½ plus with this strategy. I don't know if there will be traveling wave solution in a higher regularity space, but with this strategy, we think that we can prove existence in H3½ minus, but we cannot go further. We are quite sure about that. Let me distinguish two different scenarios. The one in which the profile bar P epsilon is just Lipschitz, non-smooth, is something with corners. This case is more easier to analyze. And then the second scenario is that one in which the profile bar P epsilon is infinity. And again, the idea here, as for the Couette flow, is to study this case, the first one, and then try to make a regularization of the profile P epsilon to find, again, something close to the Poiseuille flow. Okay? In this talk, I'm going to focus in the first case, in which the profile is something with corners. It's not Lipschitz. And this is the profile that we are going to use. So the vorticity for the Couette flow is minus 2y. Let me change the sign and look at 2 minus the vorticity of the Poiseuille flow. And then our modified vorticity is something like that. It's going to be still linear between 0 and 1/2 minus epsilon half. It's going to be flat in an interval of psi epsilon, and it's going to be again linear in the interval 1/2 plus epsilon half. Okay? Then the derivative of this profile is equal to 2 in the left side, is equal to 2 in the right side, but is equal to 0 in the middle. Okay? And then we just have to solve the equation in this part and also in this part, because in the middle the derivative of the profile is equal to 0, and we don't have to solve anything there. And this is, I mean, this is the main point here for us, that we don't have to solve the equation here. So if you look at to the H3½ minor norm of this profile bar P epsilon, well, what is the same to look at to the H1½ minus norm of this guy, you can see that making epsilon very small, you can do the norm very small, and then you are as close as you want to the Poiseuille flow by making epsilon small. Okay. So the velocity is going to be something like that. It's going to be a parabola in the on the left. It's going to be a parabola on the right, and it's going to be something linear in the middle. Okay. So what happened? So what happened is that lambda, the speed of the wave, is going to be, it must be equal to v1 at some point y star for some values of y star. This is related with the Nadirashvili stagnation point theorem. Okay, the velocity at some point, the velocity of the flow is going to be the speed of the wave, at least at a point. Okay? You cannot avoid that. But in our analysis, we cannot allow that the speed lambda is equal to the velocity v1 in a point in which we are solving the equation. Okay, we need that point out of our domain. So with a velocity like that, we can get something like this, because if the velocity, the speed lambda is over here, then the values y star is here, and then here you don't have to solve the equation, because you are in the part in which the vorticity is equal to the vorticity is constant. So the derivative of the profile bar P is equal to 0. Okay, that is the idea. I have to introduce some computation to show you why this is like this. Well, first thing that we do is that we assume that we can expand our function h on a series of cosines, and then the operator L, which is the derivative with respect to f of the functional capital F at 0, can be written as an expansion in sines. And then for this operator, each move of this operator is given by this expression. You have this term. You can think of this like the velocity v1, and then you have an integral operator with a kernel g, which is given over here. That is not very important in this talk. So the important thing is that you have something like that. Okay. And then what we want to prove in this situation is that there exists a value lambda star which is for like 1/4, such that there exists a unique solution which is C infinity in this domain, which has this form, is h1 times the cosine of x, and with boundary condition h is equal to 0 in the upper and lower boundary, and that satisfied that is in the kernel of our operator L at the point L star, lambda star. Okay, this is the result that we want to prove. We can prove, and the idea to prove it is the following. First thing is that we can assume this odd symmetry for the function h on y, and that allows you to simplify the equation. And actually, what you get is that when you are in the left side, you must satisfy this equation, but when you are in the right side, you have satisfied this equation. And here, by mu, just like, and then here you have it's not going to be very important because it's negative. You have the other guy positive. Okay, and then what is that we don't know how to solve this equation if there is a 0 here or there is a 0 here. Okay, this is the problem. So, but if this mu is less than 1 plus epsilon half, and this mu is bigger than 1 minus epsilon half, we have the zeros out of the domain in which we are solving the equation. Okay, and this is the main point in our analysis. Okay. So from now on, if you just have to remind that nu is something that depends on lambda, which is just mu squared. So mu is something that depends on mu, and the dependent is explicit. Okay. So how do we solve this equation? Well, a natural choice that you can do is you take every mode equal to 0 but 1. And I have picked the mode n equal to 1. We could do it for every mode, but well, let's take the simplest case, that is n equal to 1. So this is going to be the only one which is different from 0. And then we define this two function, well, this function capital H. That is going to be, so H is going to be H y minus mu, less than 1/2 minus, and H is going to be H y minus mu for y bigger than 1 plus epsilon. And I'm going to assume that our values mu satisfy this condition that implies that the value nu is less than 1 plus epsilon half. Okay, everything is going to be more clear in the next slide. So now we have to solve these two equations for H. Okay, this equation in the left side, this equation in the right side, and here inside the integral we have a singularity. Okay, we have a singularity with set c is equal to mu, and here we have a singularity with set is equal to nu. But if nu is in this side and nu is less than this point, then we don't have any singularity here in this equation anymore. Okay. Okay, so how can one solve a system of solutions to this system? Well, first thing that you can do is you take two derivatives in this equation, and then you get that the function h must satisfy this ODE in the left sides with boundary condition h0 equal to 0. Okay, and you do the same in the right side, and you find this ODE for the function h. So here n is equal to 1. Sorry. On the left, okay, with this boundary condition. And I noticed that the values of the function at the points 1 minus epsilon half and 1 plus epsilon half is something free, okay? So you can solve this equation by using the Frobenius method, and then you show that there is a solution for any A and B, and you plug this solution in because of course if you have a solution of this equation, you have a solution of the ODEs. But if you have a solution of the ODEs, you don't have a solution of the integral equation. You have a candidate to solve the integral equation. But you have a solution of the ODE system. You plug in the integral differential equation, and what you get is a problem like this. A matrix that depends on mu, acting on these two values, A on B, equal to 0. And then if you want to find some non-trivial solution for your equation, you need that the determinant of this matrix that depends on mu is equal to 0. And this is the equation that we have to solve. Okay? This is the equation that we have to solve. What happened is that the dependent on mu of this matrix is highly non-trivial, because if you look at over here, so this matrix depends on mu, so here explicitly, but also it's going to depend implicitly in the function h, because the function h depends on mu. Okay, is the solution of this ODE for some value from mu. So the dependent on mu of this matrix is highly non-trivial. And what can you do in order to find solution? So our strategies is to find a problem in the limit epsilon tending to 0. So let me explain a little bit what I mean with this. So let us assume that we have what we want, that we have a branch of a solution that I parameterize by epsilon. Then I have solution h epsilon and mu epsilon for every epsilon 0. We have what we want to prove that there exists. I'm going to assume that the mu epsilon is on the right of the point 1 epsilon half, and that the mu epsilon is at the left of the point 1 epsilon half. Okay? And I'm going to assume that both mu epsilon and nu epsilons tend to 0 when epsilon goes to 0. And here, very important, I am going to assume that the limit when epsilons tend to 0 of the values of the function h epsilon at the point 1 minus epsilon half and these other limits is equal. Okay, this is an strong assumption that I am doing, but let's do it. And I also assume that mu epsilon is going to be something like that, 1/2 plus mu 1 epsilon plus something that is little of epsilon. Okay? If we assume that, and I take the limits, what I get is that there is a function h0 that satisfies this ODE in both intervals, in the interval 0, 1/2 and in the interval 1/2, 1. It's not a solution at 1/2. Okay? It's a solution on one part and in the other part, but not in the point. With this boundary condition, at 0 and at 1 is equal to 0, and if you take a limit at the point 1/2, you get the same, 1. Okay? This is the solution, and this is a solution that there exists. It's a function. I mean, you can solve a system by, again, the Frobenius method. Okay? And you also get, and this comes from the fact that you really have to solve the integral differential equation. So then you also have that this function h at this value mu1 must satisfy this equation. But this is just a definition of mu1. And you can prove that given h0, always there exists mu1 that actually is in between minus half and 1/2 that satisfies this equation. Okay. Then you have an object on the limit that somehow solves your equations in the limit epsilon equal to 0. And now the question is, well, can I use this solution to find that really exists solution of our real problem with epsilon is equal to 0? And the answer is yes. And if you do an asymptotic analysis with respect to this value mu1 and this function h0, you can find that for every epsilon bigger than 0, you find a value mu that depends on epsilon and such that the determinant of the matrix mu m is equal to 0. And in addition, you are able to show that this value mu epsilon is bigger than what it has to be bigger, 1 minus epsilon half, and that the value mu is also in the part of the interval that it should be. Yeah, so let me just say something about these solutions. So if you look at here, actually we don't want to find h, capital H, we want to find this small h, okay? And then h0, capital H0 is going to be something like that, okay? So if this is the value is 1/2, small h is going to be something like this. Okay. So in the limit epsilon equal to 0, this solution does not make sense. So you don't get anything for epsilon equal to 0. You are not solving the equation for epsilon equal to 0. This is not even in L infinity. What happens is that for every epsilon bigger than 0, you open this point, you go to 1 minus epsilon 2, 1 plus epsilon 2, you find some values here of mu and here of nu. Then your solution is going to be singular at that point. Okay. But actually what you consider is the solution on that part and in this part. And then in the part in which you are solving your equation, this function is infinity and it's quite nice and you don't have any problem with that. Okay. Well, this is more or less the way in which we prove the system of this traveling wave. So that's all. Thank you.